Hello, it's Keith here, and this is lesson 5 of the ARM Thumb Assembly Programming Tutorials, and it's planned to be the last of the ARM Thumb Assembly Programming Tutorials. Today we're going to be going over the last of the maths commands you're going to need to know. We're going to be looking at logical operations and or EOR and bit clear. We're also going to be going over to the test command, and we'll be looking at the multiply command. So really just picking up the last pieces of the stuff you will want to know. Let's go over to our source code and let's have a look. Okay, so let's fire up the first of the examples and let's see it in action. So we're going to be trying the logical operations. We've got the AND command, the OR command, the EOR command, which is XOR on some systems, and also the bit clear command, which is sometimes a little bit of a rare one. So we've got all of these and they all work fine on ARM Thumb. The limitation is though that we have to use a pair of registers. We can't use an immediate value. So we've got some test values here. We're loading a test value here and a test mask, and we're going to apply the mask to the test value. The test value is 1, 2, 3, 4, 5, 6, 7, 8 in R0, and the test mask is in R1, and it's 4 nibbles of F in the low 16-bit value there. So the first command we're going to do is AND R0, R1. The destination is on the left and the masking parameter is on the right, and this is effectively R0 equals R0 and R1. Now an AND operation is going to set the bits where the source parameter and the destination parameter are 1, and this is done at the bit level. So if we just go over to the blackboard for a moment, here we go. So if we've got our source and our mask and our result, then with a AND operation, if the source and the mask are 1, the result will be a 1. But if either of the source or the mask are a 0, the result will be a 0. And of course, if they're both 0, the result will be a 0. So that is an AND operation. Very straightforward there. So you can see that that has happened just here. So this basically effectively only keeps the values where there's a nibble of an F here. The nibble has been left unchanged, but of course you could do this at the bit level. I'm just using nibbles for clarity. So that's an AND operation. Now the OR operation, OR is spelled O-R-R on ARM Thumb. So that's how we do it. And again, R0 on the left is the destination and R1 is the parameter we're using as a mask here. So this is R0 equals R0 or R1. And the effect of this is that any bit in our mask is set in the parameter after that's been applied. So our 1, 2, 3, 4, 5, 6, 7, 8 has become 1, 2, 3, 4, FF. And if we go to the blackboard, very straightforward really. So if either of the parameters is a 1, then the result will be a 1. So it's a 1 there, a 1 there, a 1 there, and it's only a 0 in that column there. So that's how the OR operation works. Very straightforward really. Next, let's have a look at something a bit more exciting. The EOR command, which I prefer to be called XOR, but it's called exclusive OR with an E here. And again, we are doing R0 exclusive OR R1 here. And what exclusive OR really means is it means flip the bits. So where our parameter has a 1 in the mask here, our source has been changed, but where it's a 0, it's unchanged. So 1, 2, 3, 4, 5, 6, 7, 8 has become 1, 2, 3, 4, A9, 8, 7. Well, why would that be? Well, that's because where our mask is a 1, the value here has been flipped. Where our mask is a 0, it's been unchanged. So this 1 flips this to a 0. This 1 flips this to a 1. But in these two cases, the source parameter is left unchanged. So we've got a 1 and a 0 there. So our second parameter, which is of course our R1 parameter in this example, has flipped the bits of our source parameter, but has left them unchanged where that second parameter was a 0. So there we go. Very handy command there. Okay. Now the final one we're going to look at is the more rare bit clear command, the BIC command. Now this is effectively sort of the opposite of an AND, where the bits are a 1 in the masking parameter here, these Fs here. Rather than the AND command which retained those bits and cleared the others, the bit clear command has the opposite, where the bits are 0 in the mask, they've been kept, but where there are 1 in the mask, they've been set to 0. So if we go over to our blackboard here, you can see that where the mask is set to 1, this source bit has been cleared. Well, this one's been cleared, but this was a 0 anyway. This bit has been left alone because it's not been cleared, and this bit is left alone, has not been cleared, so it stays as a 0. So that's how the bit clear command works. So that's what that does. Again, a good variety of commands. It's just now we're only limited to 2 parameters, and the destination is one of the 2. It's not like we've got 3 anymore where we can AND 2 together and store the result in a 3rd register. So it's more limited, but still very functional. Now, a similar command is the test command. Now, the test command is very handy. What this does is it sets the flags in the same way as an AND command would, but it doesn't change any of the registers. And I often find this is quite handy in 8-bit at least when you're reading in data from hardware, like data from a port, and you want to test some of the bits to see if you need to continue processing. And if those bits are set, then you do need to continue processing, but you need that value that you just read in still. So this will set the flags, but it won't change that value that you want to do more processing on. So the flags are set in the exact same way as an AND command would. So this is setting the flags the same as R0 and R1 would, but R0 is completely unchanged by the command. So let's try this out and let's see what happens. So what we've done here is we've ANDed the value F with the value F and set the flags accordingly. And in this case, those 2 values do not result in a 0, so the 0 flag is not set. You can see those are the flags there. The carry flag is set, but the 0 flag is not. And just to clarify that, we've branched and we've shown some symbols, and so we've shown a not equals because the 0 flag is not set by the testing of those 2 values together, effectively ANDing them. Now, if we change the test values here, this time we're going to use the test values of OF and F0, and we're going to use the test command to combine those 2 together and set the flags. So you can see here that F0 and 0F have been tested together, and the 0 flag has been set, but neither of those registers has been changed. If we had done an AND command, if we just change this to an AND command and we run again, well, the result of setting the flags is the same, but R0 has been lost in that procedure. So as I say, it's quite handy to have these test commands where you want to test the value in a register, but you don't want to change the register because you want to do more work with it later on. So yeah, that's certainly one that's worth bearing in mind. Now, another command which is relating to the flags is the commands which use the carry. In 8-bit mathematics, using the carry is very important because your registers only store 8 bits, but you often need to work in 16 bits to store your memory addresses. And the way you do this is you use the carry to pass any overflow from your low byte to your high byte. And even though the registers on the ARM are 32 bits, we can use the carry to combine a register with another register to effectively do 64-bit addition and subtraction. Now, the way this works is we do our normal add command, and if that overflows, then the carry flag will be set, and we then use an add with carry command, and we add another register to a destination, and the carry will be added to that addition. Now, just because we're only interested in simple testing here, we're setting to R4 to 0, so effectively this command is now become R0 equals R0 plus the carry. So we're going to run this addition many times and we'll see the result. Now we're loading. R0 is going to be the high part of a pair of registers, a 64-bit pair effectively, and R1 is going to be the low part, which we're loading with a very high value so it quickly overflows. You can see that here R1 equals a lot of F's and then a C, and then we keep adding 1 until it overflows from all F's to 0. At this point the carry flag will be set, and add with carry command has added that to R0, and that is the result of this command here, that add with carry R0. As I say, R4 does nothing because it's set to 0. So that has effectively allowed us to use a 64-bit pair of registers and do addition that would exceed the value capable of a single register. That's add with carry. We also have subtract with carry, in which the carry acts as a borrow. Here you can see we've got our high value still. We keep subtracting 1 until that goes below 0, and our subtract with carry has subtracted the carry acting as a borrow from our 0 there, so that again we have our 64-bit pair doing subtraction at a greater definition than a single register could manage. So there we go. It's not something I particularly have needed when I've been doing my ARM programming, because I only do little simple tests on systems, but of course I'm sure there's going to be cases you would want to do that. I'm so used to working in 8-bits that as soon as my registers reach 32-bit, my mind practically explodes. So I've never needed that, but it's there if you want it. The final command we're going to look at is the multiply command. Now the ARM has no divide command, but the ARM thumb does still retain the multiply. Very simple. 2 parameters. The parameter on the left is the destination, and it's multiplied by the parameter on the right, and the parameter on the right is unchanged. So this is effectively R0 equals R0 times R1. And you can see here that we have effectively done that just fine. So there we go. We've taken 2 and 3 and multiply them together, and the result is 6, and of course R1 is unchanged. Now I should point out that of course you can do multiplication and division if you're trying to multiply by 2, 4, 8, etc. You can do this with bit shifting, either to the left for multiplication or the right for division. That is going to be, I believe, faster than this command, so you should certainly try and use that. And of course you should try and use that for division, because there is no divide command. Now there are some tricks you can do to simulate division with multiplication commands, but that's beyond what I'm going to cover here today. It is something I've done a little bit, but I'm not really confident in it enough to describe it at this point. But as I say, that's something you can do. Anyway, that's the last of the commands we're covering today. As always, please go to my website, download the source code, and have a go with these yourself, and make sure you understand them and try them out in some more scenarios. If you've come to the ARM Thumb series without seeing the regular series, please go back and take a look at my regular series that covers the classic ARM, and of course I do have other series on other processors. I've got a RISC series, RISC-V rather. I've got 8086, the Z86, 502, 68000, all kinds of other things like PDP-11, and I'm planning a MIPS series next year as well. If you want to support my channel and you want to get some classic ARM tutorials, you can buy my book from Amazon. It's called Learn Multi-Platform Assembly with Chibi Akuma's. It covers Z86, 502, 68000, 8086 and ARM, and if it's a success I will do a book covering ARM Thumb. I have actually already started writing it, so I promise if it's a success that will come out. Anyway, if you've enjoyed this, please like and subscribe. I hope you've benefited from this. I hope you've enjoyed listening to me waffle on or something. Thanks for watching today, and goodbye.